on the definition of potential functions and conservative vector fields. So basically, we want to connect vector fields and scalar functions together. We can visualize these as follows. These are just two-dimensional vector fields that you can see, but you can use 3D grapher to visualize a 3D vector field as well. A vector field like F is called a conservative vector field if it is the gradient of some scalar function that is, there exists a function, scalar function like F, such that this vector function or vector field with capital F is the gradient of F. So on the left-hand side, you have a vector function, a vector field, and on the right-hand side, you have the gradient of F. And as you remember, when you're calculating the gradient of a scalar function, it is a vector function. In this situation, F is called a potential function for vector field F. So this scalar function has another name, potential function. Please note that not all vector fields are conservative vector fields. And you see these types of vector fields in physics and engineering. Let us go back to partial derivatives and remember that in 2 dimensions, the gradient is defined as follows. Suppose F is a differentiable function at point x and y. The gradient of F at x and y is the vector valued function nabla F, which is, it's a vector. So you basically need the vector notation. The first component is the partial derivative of F with respect to x. And the second component is the partial derivative of F with respect to y. So this helps us to verify if a given function is basically a potential function for a vector field or not. It also can be written as partial derivative of F with respect to x, I in the direction of x-axis, plus partial derivative of F with respect to y in the direction of y-axis. And remember that if you have a 3-dimensional, then you're going to add the third component, partial derivative with respect to z, and you have plus f of zk. So now that we define a conservative vector field, let us go over one example together. In this example, I give you a vector function with first component 2xy plus z. The second component is x squared, and the third component is x. I want you to verify that this function v, which is defined as x squared y plus xz, is indeed a potential function. Let us begin. We need to find the partial derivatives of this scalar function. And we need to show that if we take the partial derivative with respect to x, with respect to y, with respect to z, we basically construct these components. Take a look. The partial derivative of this scalar function with respect to x, to calculate that, you need to fix y and z. It is equal to 2 times x times y, which is basically the partial derivative of this quantity with respect to x. With respect to x again, y and z, they act like a constant. So you end up with 2xy plus, now we move on and take the partial derivative of xz with respect to x, which is going to be just z. So this is partial derivative of v with respect to x. Now let us calculate the partial derivative of v with respect to y. In that case, you have to fix x and z. This is equal to x squared. Why is that? Because in V, you only have one quantity that has y in it. The derivative of x is equal to 0. You only take the derivative of x squared y with respect to y, which is x squared. And finally, the partial derivative of v with respect to z. Now you're going to fix x and y. This is equal to, well, it is just x. Why is that? When you're fixing x and y, the derivative of x squared y is 0 plus the derivative of xz with respect to z is just x. So we found the partial derivative of v with respect to x, partial derivative of v with respect to y, partial derivative of v with respect to x. This is the visualization of this vector field in the space. A vector field is represented by small arrows. Sometimes we scale this to make it a little bit nicer, but since this vector field is not scaled, I just graph it as it is. Now our conclusion, since f, our vector field, is defined as 2xy plus z as the first component, x squared as the second component, and x as the third component, as you can see, it is indeed equal to the gradient of v. The partial derivative of v with respect to x is the first component of f. The partial derivative of v with respect to y is the second component of f, and the partial derivative of v with respect to z is the third component of x. What's the meaning of that? It means that v is a potential function for f, and f is a conservative vector field.